それではアシュクロフトマミン始めます。それでテキストブックはここにあります。これです。それでこれだいたい30ページぐらいで、ちょっといろいろ一番は考えることはあったんですけど、もうこれぐらいにしときます。で、2番のジュールヒーティングに移ります。Joule heating. Consider a metal at unit temperature in a static uniform electric field E. An electron experiences a collision, and then after a time t, a second collision. In the Drude model, energy is not conserved in collisions, for the mean speed of an electron emerging. This is the important part, I think. Energy is not conserved in collision in Drude model. For the mean speed of an electron emerging from a collision does not depend on the energy that electron acquired from the field. Since the time of the preceding collision, the mean speed of an electron emerging from a collision does not depend on the energy that the electron acquired from the field. Since the time of the preceding collision. Assumption for page 6. Part A, show that the average energy lost to the ions in the second of two collisions separated by a time t is EET square divided by 2m. The average is over all directions in which the electron emerged from the first collision. This is kind of difficult. Show that average energy lost to the ion in the second of the question is whether we are assuming three-dimensional case or one-dimensional case. But it says average is over all directions in which the electron emerged from the first So let me make whiteboard. Whiteboard box. I don't know if I can. This is scary. So there is a first collision, or whatever the direction. This is the x. Any direction. Okay, there is a first collision. Okay. I think we just consider first collision. Okay, we just have first collision, then this go all directions. All directions. Each direction there is a second collision. Second collision, something like this. Okay, then what's that? Okay, then there is a specific electric field. Let's see, this is electric field. So that average energy lost to the ion in the second of two collisions, separated by a time t. Let me see. Just assume this electron has energy. Electron has energy of 1/2 mv squared. This is energy, right? Then what kind of energy? Okay, so let me see. I can do this. This is v vector square. Yeah, and let's forget about plus and minus for the moment. It's just make complication. So we consider what is the acceleration. Okay, acceleration by E. Okay, acceleration. This is like MA. This is the acceleration is. Let me see. MA equal E. Alright, so A is MEE. So then for time t, V goes like V plus AT. So this is like V plus MET. Okay, so the energy change, I would say the energy change is 1/2 m. V plus METE square minus V square. So let me write this part delta vector. Okay, so this is like 1/2 m V square plus is this I forgot, A dot B, is this same as B dot A? I'm confused. I think it is. I think this is B. So this is 2 v delta dot delta plus delta square minus v square. So this is 1/2 m I would say this is 2 v dot delta plus delta square. Yeah. So then we average over all direction. So if we average, this is all direction. All direction. This is one direction. So by averaging we obtain, this is 1/2 m delta square. That means MET 1/2 m MET square E square. Okay, so what is our question? 2m EET square. So this is 2m EET square. That's it. So part A, this is part A. Part B, show using the result of problem 1b, that the average energy loss to the ions per electron per collision is, hey, 2 missing, E tau square divided by m, and hence that the average loss per cubic centimeter per second is blah blah blah. Deduce that the power loss in a wire in length L and across section A is I square R, where I is the current flowing and R is the resistance of a wire. What is the problem 1b? Show that the probability that the time interval between two successive collisions of electrons falls in the range between t and t plus delta t. Okay, so okay. So let me show delete. Okay, this is okay. This is fine. So this is the Hey. Oh. This is how we do. Seems like I have to delete partially. Partially, I have to erase partially, then I can reset. So let me see. This is the collision rate. Okay, dt over tau exponential minus t over tau. This is the collision rate. Okay, so then we have to average. What is the probability? This is absolute probability. So this is a probability. Then the energy loss is, what was this? Energy loss is EET squared over 2m. EET square over 2m. This is the energy loss. We integrate from 0 to infinity. So we just put all constant outside. So tau 2m tau outside, and EE square, this is outside. Then we have 0 to infinity, and t square e to minus t divided by tau. Is it okay? Then dt. Okay, so then we just set t, change variable, like t prime is tau t. Okay, so then t is tau t prime. So you have tau square outside, then this become prime, and this become prime, then dt, then we have tau q, then this dt prime. Then we can go to Wolfram alpha. Let me see. How do you do this? This is should be integrate, and なんだっけ x, I go by x square times exponential minus x, from 0 to infinity. How about this? X square e to minus x. So this is the 2. So then we can do, we found this part is 2. Then equal. So we can cancel this way. Then 2 cancel. So I can do n e tau square. So this is this. We have the loss to the ions per electron per collision is this, E tau square divided by 2, and hence that the average loss per cubic centimeter per second why is this so? Average loss per cubic centimeter per second. This is collision. Let me see. So energy loss per unit cubic centimeter, unit volume, energy loss per unit volume is like this. You have how many electrons? You just multiply number of electrons, n times m e tau square. This is a number. This number of electrons. So then we just, this is the number of collision. This is number of collision per unit time. I think this is it. So this is, you can calculate m n e square tau. Correct? Okay. N e square tau e square. N e square tau e square divided by m. Same. So then sigma, or sigma 0, I think. Sigma 0 is like m n e square tau. So this is like sigma 0 e square. Is that right? Sigma. I think AshcroftMermin called this sigma 0. Yeah. So I can call it. This has to be sigma 0. Deduce that the power loss in a wire in length L and cross section A is I square R, where I is the current flow, and R is the resistance of the wire. Let me see. Okay, what is the energy loss? Per sec. This is AL times the quantity I just calculated. Sigma 0 E square. And then sigma we can put resistance. Resistance equal inverse sigma 0 divided by A multiplied by L. Okay, so then sigma 0 is R 1 over R AL. Okay, then we can also place E is, what's the quantity we use? Power loss I square R. We can use I. We can use I if I want to. But we have to convert E. Anyway, I equal V over R. Is it correct? V over R. And this is V is EL. E times L divided by R. Okay, so we can obtain E equal IR divided by L. So I put all of this here. AL times sigma is R 1 over R AL. E square is L square I square R square. So R L square. So I obtain I square R. Okay. So I can move on to next question, maybe next time. So see you.